Nobody invented electricity, and the question is worth asking anyway, because the honest answer is more interesting than the one it seems to be looking for. Electricity is not a device. It is a property of matter, built into the structure of atoms, and it has been operating continuously since the universe cooled enough for atoms to exist. It holds every molecule in your body together. It is what makes solid objects solid. When your hand meets a table, what stops it is electrical repulsion between electrons, not any physical contact in the way we imagine it. Every thought you have ever had was an electrical event. Lightning has been striking the Earth for billions of years, and electric fish were generating meaningful voltages long before anything resembling a human existed. So the actual question is when humans noticed electricity, when they worked out what it was, and when they learned to produce and control it on demand. That story runs from a piece of fossilized tree resin picked up on a Baltic beach to a global machine that has to balance supply and demand every second of every day, and it contains one of the strangest chapters in the history of medicine along the way. Let's dig into this properly, because the noticing came first and took a remarkably long time to go anywhere. The Greeks knew that rubbing amber with cloth or fur made it attract light objects, feathers, dust, hair. Thales of Miletus is traditionally credited with recording the observation in the 6th century BCE. The Greek word for amber is electron, and roughly 2,000 years later, William Gilbert, physician to Elizabeth I, coined a Latin term from it to describe substances that behaved this way. That is the direct source of the words electricity, electron, and electrode. Gilbert did substantial experimental work distinguishing this attraction from magnetism, which had been confused with it, and he is a reasonable candidate for the first person to study the subject systematically rather than as a curiosity. For those two intervening millennia, static electricity was essentially a parlor trick. It could be produced, it could be demonstrated, and it could not be stored, directed, or made to do anything useful. There is a well-known artifact sometimes offered as an exception, a set of clay jars from near Baghdad, containing a copper cylinder and an iron rod, which have been proposed as ancient batteries. Replicas can produce a small voltage when filled with an acidic liquid, but the interpretation is contested, and the mainstream archaeological view leans toward there being storage vessels for scrolls, with no supporting evidence of wires, conductors, or any application they could have powered. It makes a wonderful story, and the evidence for it is weak. Let's talk about what is actually moving too, because this represents a point where almost everyone's mental picture is wrong in a way worth correcting. The common image is of electrons racing along a wire from the power station to the appliance, and very little about that is right. In a typical household circuit carrying alternating current, individual electrons do not travel from one end to the other at all. They oscillate back and forth around a fixed position many times per second. Even in a direct current circuit, the average drift speed of an electron along a copper wire is astonishingly slow, on the order of fractions of a millimeter per second, slower than a person walking. What travels fast is the electromagnetic field, and it does so at a substantial fraction of the speed of light. The usual analogy is a pipe already full of water. Push at one end, and water emerges from the other almost immediately, even though no individual molecule crossed the distance. Energy is carried by the field surrounding the conductor rather than by the particles inside it, which is why the geometry and spacing of wires matters so much in high-frequency work and why the electrons themselves are best thought of as the medium rather than the message. It also explains why a light comes on the instant you flip a switch, despite the electrons in the filament having barely moved. Let's talk about the 18th century too, because this represents the period when electricity stopped being a curiosity and became a science. Machines were built to generate static charge in quantity. Spinning glass globes, or discs rubbed against pads, producing sparks large enough to be dramatic. Then, in the 1740s, came the Leyden jar, developed independently by more than one experimenter, which was the first device capable of storing electrical charge. It is a glass jar with conducting foil inside and out, and it is a capacitor, though nobody used that word yet. Charge it from a friction machine, and it holds a substantial quantity, releasable in a single, sharp discharge. Suddenly, electricity could be accumulated and delivered at a chosen moment, and the effect on the field was immediate. Public demonstrations became popular entertainment, and there is a famous account of a French experimenter discharging a jar through a long line of monks holding hands, all of whom jumped at once, which was both a spectacle and a genuine experiment in the speed of transmission. Benjamin Franklin's contribution belongs here and is frequently misremembered. His significance is not that he discovered electricity, which was already well known, nor that he was struck by lightning, which he was not. What he did was propose and help demonstrate that lightning and laboratory electricity are the same phenomenon at different scales. A serious hypothesis at a time when lightning was widely understood in other terms. He also introduced the framework of positive and negative charge and the idea that electricity is a single fluid transferred between objects rather than two distinct substances. And while the details of that model were later superseded, the sign convention stuck. The lightning rod followed directly from the work and is one of the earliest examples of theoretical physics producing a device that saved a substantial number of lives and buildings. Let's talk about the first commercial use too, because this represents an application that arrived decades before anybody lit a house with electricity. The telegraph came first, and it mattered enormously. Once Ørsted and Faraday had established that current could move a needle and that a coil could act as an electromagnet, sending a signal down a wire became a straightforward engineering problem. Working systems were operating in Britain and the United States by the late 1830s and 1840s, and within a few decades, cables had been laid across the Atlantic seabed after several expensive and demoralizing failures. The consequence is difficult to appreciate now. For the whole of history until that point, information traveled at the speed of a horse, a ship, or a runner, which meant news from a distant place was necessarily old news, and a message and its reply were separated by weeks or months. The telegraph broke the link between the movement of information and the movement of a physical object for the first time. Markets in different cities began to share prices within minutes rather than days. Armies could be directed from capitals. Railways could be coordinated safely on shared track. Newspapers could report events from other continents while they were still happening. Every subsequent communication technology, telephone, radio, television, the internet, is a development of the same break. And it happened because a compass needle twitched during a lecture. This detail is worth sitting with directly because the next major advance came out of an argument about frog legs. In the 1780s, Luigi Galvani, an Italian anatomist, found that a dissected frog's leg twitched when touched with metal instruments under certain conditions and concluded he had found evidence of an intrinsic animal electricity, a vital force residing in living tissue. Alessandro Volta, a physicist, disagreed. He argued the electricity was not coming from the frog at all, but from the contact between two dissimilar metals, with the moist tissue serving merely as a conducting medium. To prove it, Volta built a device with no biological material whatsoever, alternating discs of zinc and copper separated by cardboard soaked in brine, stacked into a column. It produced a steady, continuous current. That device, reported in 1800 and known as the voltaic pile, is the first true battery, and it changed everything. Every electrical device before it worked on static discharge, a brief, violent release. The pile produced sustained current that could flow for hours through a circuit. Within weeks of the announcement, researchers across Europe were using piles to decompose water into hydrogen and oxygen, and within a few years, Humphrey Davy had used much larger batteries to isolate several chemical elements for the first time, effectively founding electrochemistry. Galvani, incidentally, was not simply wrong. Bioelectricity is entirely real, and nerve and muscle function do depend on electrical signaling. Both men were partly right, and the dispute produced more than either position would have alone. Let's talk about the connection to magnetism too, because this represents the single most consequential discovery in the whole story. In 1820, Hans Christian Ørsted, a Danish scientist, noticed during a lecture demonstration that a compass needle deflected when a nearby wire carried current. Electricity and magnetism, treated as separate phenomena, were linked. The implications were pursued immediately, and rapidly. André-Marie Ampère developed the mathematics of the forces between current-carrying conductors within months. And Michael Faraday, working in London, asked the reverse question. If a current produces magnetism, can magnetism produce a current? In 1831, he demonstrated that it can. Moving a magnet relative to a coil of wire induces a current in that wire, an effect called electromagnetic induction. It is difficult to overstate what follows from this. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Induction is the operating principle of the electric generator, which converts mechanical motion into electrical energy, and of the electric motor, which does the reverse, and of the transformer, which changes voltage. Essentially, all electricity generated anywhere in the world today, whether the turbine is spun by steam, falling water, or wind, is produced by Faraday's principle. Faraday had almost no formal mathematical training and worked largely through physical intuition and experiment, developing the concept of fields of force to describe what he was seeing. James Clerk Maxwell then supplied the mathematics, publishing in the 1860s a set of equations describing electric and magnetic fields and their interaction. The equations produced an unexpected result. They predicted waves propagating through space at a speed that matched the measured speed of light, leading Maxwell to conclude that light is an electromagnetic wave. Heinrich Hertz later generated and detected such waves experimentally, confirming the prediction and opening the path to radio. Within a few decades, electricity had gone from a curiosity involving rubbed amber to a unified theory that explained light itself. Let's talk about the electric light too, because this represents where the science reached ordinary households. Arc lighting came first, producing intense light by sustaining a spark across a gap between two carbon electrodes, and it was used for streets, lighthouses, and large spaces. It was far too bright and too crude for a home. The incandescent lamp was the domestic solution, and its history is a good corrective to the single inventor story. Many people worked on heating a filament inside a glass envelope, including Humphrey Davy decades earlier, and Joseph Swan in England developed a working lamp and was demonstrating and installing them around the same period as Thomas Edison in the United States. Edison's decisive contribution was less the bulb itself than the recognition that a bulb is useless without a system. Generating stations, distribution networks, meters to bill customers, switches, fuses, sockets, and a business model. His organization pursued all of that, and the resulting infrastructure is closer to his real achievement than any single component of it. Let's talk about the current war too, because this represents a genuine technical dispute that got settled by physics rather than by rhetoric. Edison's system used direct current, where charge flows steadily in one direction. Direct current has a serious limitation. Transmitting it over distance at usable voltages produces heavy losses in the wires, meaning generating stations must sit close to the customers, which requires an enormous number of them. Alternating current, where the flow reverses many times per second, has a decisive advantage. It can be stepped up to very high voltage for transmission, which drastically reduces losses, then stepped back down for safe use, and the transformer that does this works only with alternating current. Nikola Tesla developed practical alternating current motors and polyphase systems, and George Westinghouse commercialized the approach. The competition between the camps was aggressive and included public campaigns emphasizing the dangers of high-voltage alternating current, some of which involved public electrocutions of animals, a grim episode that is well documented and reflects poorly on those involved. Alternating current won on the engineering merits, and the grid that exists today is built on it, though high-voltage direct current has since returned for specific long-distance links where its own advantages apply. Let's talk about the grid too, because this represents something arguably more remarkable than any single invention in the story. Electricity is difficult to store in large quantities. which means a power system must generate very nearly exactly as much as is being consumed, continuously, in real time. Demand changes constantly as people switch things on and off, and supply has to track it within tight tolerances, since a mismatch shows up immediately as a shift in frequency that can damage equipment and cascade into blackouts. The system that manages this is enormous, automated, and largely invisible, and it is reasonable to describe an interconnected national grid as among the largest machines ever built. The growth of renewable generation has made the balancing problem harder rather than easier, since output from wind and sunlight varies independently of demand, which is why grid-scale storage and demand management have become such active areas of engineering. Let's talk about standards too, because this represents the reason a traveler carries a bag of adapters, and the explanation is entirely historical rather than technical. Electrical systems were built out nationally by competing private companies and public authorities during a period when nobody was coordinating internationally and nobody expected appliances to cross borders. Each system settled on whatever voltage and frequency its engineers and equipment favored, and once a country had wired a substantial number of buildings, changing the standard became prohibitively expensive. The result is a world broadly split between systems running at roughly 100 to 120 volts and those running at around 220 to 240, with mains frequency generally at either 50 or 60 cycles per second depending on region. There are real trade-offs between them rather than a clearly correct answer. Higher voltage delivers a given amount of power at lower current, which permits thinner and cheaper wiring and reduces losses within a building. Lower voltage is less dangerous on contact. Plug and socket designs then multiplied on top of that, with many incompatible patterns adopted for reasons involving patents, national manufacturing interests, and safety philosophies. And attempts at international standardization have largely failed against the sheer cost of replacing installed infrastructure. It is a good illustration of how technical systems get locked in. The decision was cheap to make once, and is now effectively permanent. Safety engineering developed alongside, and is worth noting because it is almost entirely invisible when working. Fuses and later circuit breakers interrupt a circuit drawing more current than the wiring can carry, preventing conductors from overheating and starting fires. Earthing provides a deliberate, low-resistance path to ground so that a fault energizing the metal case of an appliance trips the protection rather than waiting for a person to complete the circuit. Residual current devices compare the current flowing out against the current returning and cut power within milliseconds if the two differ, on the reasoning that the missing current is going somewhere it should not, quite possibly through a person. Insulation standards, socket shutters, and polarized or earthed plug designs all address specific documented failure modes. Domestic electricity remains a leading cause of accidental fires and electrocution, and the gap between how dangerous it is and how safe it feels is a direct measure of how much engineering sits between the grid and the socket. Let's talk about electric fish too, because this represents a strand of the story that ran alongside everything else and fed directly into it. Long before anyone rubbed amber, people in several parts of the world knew that certain fish could deliver a shock. Egyptian sources depict the electric catfish of the Nile, and Greek and Roman writers described the torpedo ray, whose numbing discharge was used deliberately in ancient medicine, applied to patients to treat headache and gout, which makes it arguably the earliest recorded therapeutic use of electricity by well over 1,000 years. Nobody involved understood the mechanism, and the effect was generally described in terms of a mysterious numbing power rather than anything resembling a current. The connection was drawn properly in the 18th century when researchers realized that the shock from a torpedo ray or an electric eel behaved like the discharge from a Leyden jar. That identification mattered a great deal because it established that a living organism could produce the same phenomenon being generated in laboratories, and it fed directly into the arguments Galvani and Volta would have about animal electricity. The animals themselves turned out to work on a principle Volta would have recognized immediately: stacks of specialized cells called electrocytes, arranged in series so their individual small voltages add, which is structurally very close to what the voltaic pile does with metal disks. An electric eel can generate several hundred volts using an arrangement it arrived at through evolution, And Volta is sometimes said to have had the eel's anatomy in mind when designing his own stack, though how directly it influenced him is debated. Let's zoom out and pull all of these different threads together. Electricity was never invented, because it is a fundamental property of matter that predates the Earth. What humans did was notice a strange behavior in rubbed amber, name it after that amber, and then spend 2,000 years failing to do anything with it. The 18th century brought generation and storage of static charge, and Franklin's demonstration that lightning is the same phenomenon. Volta's pile in 1800 delivered continuous current for the first time, out of an argument about whether twitching frog legs proved the existence of a vital force. Ørsted linked electricity to magnetism in 1820, Faraday discovered induction in 1831, and thereby gave us the generator and the motor. And Maxwell's equations in the 1860s unified the whole subject and revealed that light itself is part of it. Practical lighting and distribution systems arrived at the end of that century, and the argument between direct and alternating current was resolved by the physics of transmission losses, which leaves an interesting thought worth sitting with. The gap between noticing electricity and understanding it was about 2,000 years. The gap between understanding it and building a civilization that stops functioning entirely without it was about 100.